Hello everyone, welcome to Science Diggers, a show where a bunch of friends dig into the history of science. Every episode, we review and discuss one paradigm altering observation. We bring to you our discussions on these milestones. And this episode, we're talking about the paper titled Experiments on the Effect of a Current of Electricity on the Magnetic Needle, written by John Christian Ørsted. In English, the name Ørsted is pronounced as Oersted, or as the Google Translate says, it's pronounced as.
Ørsted.
But then he's a Danish physicist also, but maybe I would rather call him a Danish natural philosopher. And in Danish, it's pronounced as.
Ørsted.
So we can't promise you good pronunciation over the entire episode, but I hope you'll bear with us. So this paper was the first to point towards the direction of merging or unifying the electricity and magnetism. Before proceeding any further, let us introduce ourselves. I'm Vidya Sagar, and I'm studying particle physics in University Paris-Saclay.
Hi, I'm Bhavesh. I'm studying optics and photonics in KIT, Germany.
And my name is Adityan, and I'm studying quantum engineering MSc at ETH Zurich.
Hi, I am Pratyush. I am studying Masters in Particle Physics at ETH Zurich.
Okay, so this is where, since our paper is being discussed on the magnetic effects of current, I would want to initiate by setting up some context and history about this paper. Now we're talking about the year 1820, which is exactly 200 years from now, in the past. So I would like to set up the context to how research and developments before this led up to this discovery. So we'll start with the idea that there already existed magnets in the form of lodestones, and we had something like static charge by rubbing of two substances from a long time, which was say 600 BC. Now static electricity was being explored in the 16th 17th century, and as we go on to the 18th century, this is where our first interesting object comes in, which is the Leyden jar. So this was 75 years before this said discovery, where they had something like a capacitor where rubbing would cause it to charge, and if you touched it, there was discharging. So this was also the inspiration for Benjamin Franklin's famous kite experiment. Now 2 years from this time, Cavendish started the first experiments where the static electricity was being discharged, which causes current. So this immediate current was being used to study conductivity of different elements or materials. Now in 1785, which was 35 years before this experiment, Coulomb was doing his research on separate charges, which as we now know is called the Coulomb's laws, where the force between two different static charges depends on the extent of these charges and the distance. Now 1780, about 40 years before this experiment, we have the famous experiment, which is an accidental experiment by Galvani, which is called the frog leap experiment. Now this is where we could have some interest on how current flow was being studied. What happened was Galvani took frog limbs of a dead frog, and he connected metals of two different kinds to different parts of the limb. Now if these two metals were brought into contact, what was observed was the legs twitched. Now in around 10 years, what Galvani proposed this to be called as animal electricity. Well, eventually it was found that different metals have different affinity towards electrons, and this relative affinity causes current to flow. So it was not actually that the animals had current, but rather it was the current which was flowing because of the metals. Now our most interesting experiment which happened before this was when Alessandro Volta discovered the voltaic or galvanic cell. Now why this is interesting is because this was the first time when electricity happened to be in a steady flow. Until now we had talked about static charges and how bringing them in contact we could see an immediate flow of current. What we see here is that Volta had in 1800, which was 20 years before this experiment, invented a way in which we could have a steady flow of current. And this is the voltaic or galvanic cell which was used by Ørsted in his experiment. There's also an interesting discovery done by an Italian philosopher whose name is Gian Domenico Romanozzi, but we'll come to this eventually in our discussions.
But Bhavish, you mentioned that Galvani observed a flow of current instead of static charges that was known so far. Are you sure that he used the word flow? Do you think he realized the concept that this was basically static charges but flowing, or do you think this he observed it? I personally believe he observed it to be a different phenomena which had some sort of electric relation, because when you put something that is conductive, people realize what materials were electrically conductive and what materials weren't electrically conductive long before this. And when you put an electrically charged or a conductor near this frog experiment, it had some effect on it. So they realized that it was something to do with electricity. But do you think Galvani at this point already realized that this was the same electric charges that were moving, or do you think that he realized the flow, as you call it?
So, at least from what I understand, Galvani, when he called, as I've mentioned, he called it something animal electricity. He also called things material electricity. So, at this point, Galvani does not seem to have understood about the idea that we could attain something like a steady flow, because all his experiments indicate he had worked with impulses of electricity. So, I do agree that steady flow is not something we can bring into exact discussion here, and since this was more of Volta's work where he looked at the battery, I think we can call it a steady process even in their understanding. So I suppose that
Yeah, I
covers.
think from what I understand, it was 1 year later, 1 year after the Galvani's experiment, that some French physicist or French natural philosopher, because back then there was no such thing as physicist, yeah, French natural philosopher called Jacques Bisson came up with the word electric current. I think that was when they started using the word electric current. But I think not everyone were convinced that this is the electric charges moving. So I think that was the main difference between the term electricity, which was the study of charges, and galvanism, which was the study of something that is happening in this galvanic experiment. They weren't really sure that this is the same thing as electric charges moving. But yeah, something I found interesting was before Galvani, the only electric related phenomena that they observed was the electric charges produced, the static electricity produced by friction, all sorts of friction. They even have had a machinery that was created to generate static electricity. It was basically two conductors rubbing each other. So there was a grinder, something like that, where you turn it around and then so you produce a current, electric charges between these two plates, and then they use these electric charges to do all kinds of experiments. But Galvani's experiment was the first of its kind, because it was the first ever observation of electric current, or as they call it, galvanic current or galvanism. Before that, everything that they observed was static electricity. And because Galvani observed it in animals first, he called it animal electricity. But obviously, that led to so many misinterpretations among so many other people, primarily philosophers in spiritual philosophers and stuff like that, where they started believing that only animals are capable of generating electricity or generating this galvanism. Only animals were capable of generating electric current, as we call it now. And they came to conclusions as such that it is the essence of life. It is what makes life different from everything else. It is the soul. And also, it becomes even more interesting when they started realizing, obviously, the other phenomenon observed before Galvani was the lightning. They realized that it had something to do with electricity. And obviously, Benjamin Franklin had something to propose that it was basically electricity in the clouds or in the sky. But after this Galvani's experiment, they started really believing that it was galvanism that is happening in the sky. It is the electric current that is happening in the sky, and only animals or only something with life can do that. Hence, there is life in sky, or what kind of what these line of thought leads to. So yeah, there was a lot of such misinterpretations that electric current has something to do with life itself. And Alessandro Volta was against it. He did not believe that this thing can be related to animals or life as such, and he wanted to disprove it. And the primary motivation, so this motivation to disprove Galvani and his interpreters saying that life has something to do with electricity is what led him to invent this electric battery, or voltaic pile as he called it. And so yeah, he basically created electricity, or this galvanic current, completely out of chemicals, completely out of inorganic objects, so completely out of something you extracted from earth, something which had no life. So that's how he disproved Galvani and his interpreters. And I still find it interesting that despite his attempts to disprove Galvani, his invention is called Galvani apparatus or galvanic pile. A lot of credit has been given. I mean, like, I believe Galvani deserves credit for observing the electric current for the first time, but I find it interesting that he invented something and named it after the person whom he wanted to disprove it. But yeah, and if you guys ever find something out interesting, or if you discover or invent something, what do you think you'll name it? Or what do you think you'll name it after?
It depends on the stuff that you are inventing, right?
Yeah, sure. Like, but do you have any certain person you want to name it after, or something like that?
Pratyush, do you want to answer this?
No, I'm not that selfless, so I'll name it after myself.
Yeah, I would.
Good answer.
Cool.
Yeah.
And yeah, I personally think so. I had a high school teacher in my 9th, 10th class standard. His name was Joshi, and to inspire us to show us what kind of pride this field of research gives us, he tried to motivate us by saying that he wanted to discover a new element in the periodic table and wanted to call it Joshilivium. His name was Joshi. So I think if I invent or discover something eventually, I would like to dedicate something to him. I would call something Joshi something, depending on how that field of science names things. Yeah, I would try to have something related to Joshi.
Okay. Nice.
That
Yeah.
reminds me of a funny trivia from mathematics. It said that most of the famous theorems in mathematics, which is associated with the name of a mathematician, was actually not proved or was not actually found by the same mathematician. Like Euler's theorem or whichever famous theorem you can think of, it's actually wasn't first discovered by the said mathematician.
Mhm.
Just a trivia.
Nice.
Nice.
So yeah, moving on. So when I was describing the whole concept of this episode, this podcast to my dad, he mentioned I was describing about how beautiful the story of Galvani and Alessandro Volta was, and how revealing that was to the people who were misinterpreting stuff for 20 complete years and then realized something else was happening entirely. And my dad pointed out that he heard of something called Baghdad battery, which is found in a certain Arabic country around 2000 years ago. So it was found in, I think, around 1800s by an archaeologist, and when he realized that it was 2000 years ago, and he realized that it was basically a clay pot with two electrodes in it, a copper and iron electrode. And they believe, based on the sediments left on the clay pots inside, they believe the internal they contained either vinegar or grape solution internally. And it is obvious for us now that it would act like a battery, because there are two electrodes, two differently conductive metals inside, and grape juice and also vinegar are really good electrolyte solutions. So this technically is a battery. But do you think they invented the battery 2000 years ago? Well, right now, the battery we're talking about, the Alessandro Volta's voltaic pile, is around 220 years ago from now. It's 2020 this time, right now. So 220 years ago right now, in 1800. But this Baghdad battery dates back to 2000 years ago. Do you think they invented the battery?
I would personally be of the belief that since it qualifies for all requirements which we have in terms of having a voltaic cell, this does look like a battery to me, since it will provide at least to a certain lifetime as a current source, which will of course decay, but that is the same as what we have in our voltaic cell. So to me, it sounds like a battery, honestly. Although I still have to think of where would these Baghdad batteries be used. Was there
Exactly,
anything on
yeah.
those lines?
Yeah. So yeah,
Exactly.
even
So I think Bhavesh mentioned something in the introduction about the philosopher Romanozzi. So I think his idea, or maybe his observation of seeing the deflection, he might have seen the deflection, but it went unnoticed because maybe the society wasn't up to date with, maybe because the electromagnetism wasn't up to date with what he found. So similarly, the Baghdad battery, I think maybe they found it, but people didn't know what to do with it. So you might find, yeah.
And I was saying maybe they used a series of Baghdad batteries to execute people or electrocute people. You don't know.
yeah, we'll come back to Romanosy topic later on once we discuss what the paper is itself. And yeah, so definitely. So I completely agree that these Baghdad people, the people from Baghdad, obviously made a battery. It is definitely a battery, but that doesn't mean they invented a battery. Unless they realize what it is and how it is supposed to be used, I wouldn't call they invented the battery. And yeah, so I think the primary arguments from the people who believe that it was a battery and they invented the battery was they used it in series or parallel collections and to make it more powerful, and use it for electroplating, for jewelry and all kinds of sculptures. Not electrocute people, because that needs so much voltage and so much current that I'm not sure they can. I'm still surprised at the fact that they had a room full of electronic components to make the first early computers. So I'm not sure they had a room full of Baghdad batteries to, electrocute people. I think that's too much. They had so much poison around all the time. I think a lot of things they had around was poison, so it was easy to kill people. Otherwise, other than through electrocuting people with such a high current. But so yeah, I think I was thinking about how to give credit, and I was reading more about it, and then I found a way of giving credit. So when do you say a person P discovered some phenomenon X? So what I found is it needs to satisfy 4 conditions. 1, X does really occur. That is, X is true. If not, there is no point in giving credit. 2, P did really find X. So P found the X properly. P is the person. So that person particularly found the phenomenon X. And third condition is P was the first to find X. The person was the first to find X. And fourth is P interpreted X correctly. So I agree that this was a battery, and I agree this works, and I agree that they had it during 2000 years ago in the Baghdad, but I don't think they interpreted it correctly, because if you think of it, for us it seems obvious that you can connect a few batteries in parallel and series to increase the power, but that is not really an obvious thing to find out. It needs a lot of certain set of ideology, certain set of fundamental laws you need to know before to come up with Kirchhoff laws, or to come up with the fact that you can just connect them in series and parallel to increase the voltage and current. So I'm sure that they didn't have such ideology of connecting batteries in series and parallel back then. Well, to start with, they didn't have these electrodes popping out of the pots out itself. It was all concealed. So I don't think they used it in any way. So probably they just realized that if you put an electrode in a particular solution for a long time, the solution tastes differently. I think you already know why. And I think they were trying to make the wine taste better, or the vinegar taste different, by putting some electrodes in it, but I don't think they used it as a battery. So I think they made a battery for sure, but I don't think they invented the battery. And there's this YouTube video by a channel called Electro Boom. It was about the Baghdad battery, where he actually tries to make a Baghdad battery and try to put it in series, and he tries this how much voltage and how much current it can supply. And it was mostly a rant about how Baghdad battery is not an invention. It was mostly accident, to say.
So I had a few things to add. First of all, your third and fourth condition, which you have mentioned about what counts as a discovery or for an invention, say, does not seem to be satisfied by a lot of actually actual credits given for inventions or discoveries. I mean, even in our further discussion, we're gonna have the talk about Ørsted versus Romanozzi, which is again a condition which is not satisfied. So I would rather say,
We will, definitely come to Ørsted versus Romanozzi. But yeah, I agree that in this field or in the field of anything, miscrediting happens a lot. But if you have strong arguments against the credit, you can definitely bring it up. But we should have certain logical requirements to differentiate credits. I think this stands as a good set of requirements. Maybe once we start talking about the Ørsted case, maybe we can discuss more about how valid these requirements for crediting are. So coming back to the paper of discussion here, that is the Ørsted paper describing how he observed that battery or the current passing through the battery had an effect on the magnetic needle nearby. So Ørsted was teaching galvanism and electricity to a class, and this was during a class demonstration. He was demonstrating how the galvanic apparatus or a battery works. And he happens to have a compass around, and he realized that the compass needle, the magnetic needle in the compass, was moving when it was placed parallelly below the wire of the galvanic apparatus. So he realized that when a wire with current passing through it was parallelly above the needle, exactly above the needle, the end next to the negative terminal of the battery will go westwards. So this angle of declination, he also observed with more observations. He later realized that this angle of declination, the angle it moves, is dependent on the distance between the wire and the needle, and also the power of the battery. And he tried to move this battery sideways in the same direction. So instead of just putting the wire parallelly above the needle, he tried to move it a little. And then he realized that when it's moved, the effect is still observed. It's just that the angle that the needle moves is less now. So he realized that it's not a simple attraction or repulsion between the wire and the needle, because if that's the case, when you move the wire one way, it should attract, and if you move the wire other way, it should still attract. It shouldn't repel another way. And he tested this with various different types of materials for the wire, all kinds of conductors that they knew that they could make wires out of, and he tried to mix and match as well. He tried to make a wire out of both gold and brass together, and then he tried to put different layers of material between this wire and the needle to see if this can be propagated through this material. So he tried both conductors and insulators. He realized that with wood or glass, which are insulators, this effect was still observed. But if you put a metal sheet between the wire and needle, the effect is still observed. That means that even conductors that can conduct electricity are still propagating this effect. So he realized that this is not a simple electricity. And he tried to put the wire under the needle. And this time, the needle started moving in opposite direction. And also he realized that the needle started deflecting in the opposite direction when the current was reversed. And he realized that needles of other material don't have the same effect. Only a magnetically active needle had this effect. So he realized that there was something to do with magnetism in this. So yeah, that was primarily his observations. And so he concluded by calling this a current conflict or electric current conflict. So he concluded by calling it electric conflict, which travels in circles or spirals around the conductor based on his observations of how the relative position of current and the needle work. He called it electric conflict in circles or spirals around the conductor. And hence started the first ever realization that there is some kind of effect that both unifies the electric and magnetism.
So, yeah, I'm not sure about the exact date, but as you mentioned, the spiral motion related to what he observed. So, I think there was a correlation between the electric fields and fluids. So, basically, there are people who have stated a fluid model of a fluid model of fields. So just like uh, just like in fluids we have vortices, liquids we have vortices, somewhat correlating it with magnetic field lines and replacing the vortex with a charge. So this was just an observation, but nothing was concrete at that point of time. Yeah, so it reminded me when he mentioned the term spiral, but I'm not sure. I'm sure that it was before the experiment, but I'm not sure exact date. Yeah.
So are you saying that it's like this was the inspiration behind Ørsted to, hypothesize that it has to be in spiral?
Uh, I think the spiral notion also, there's one more thing which I think could have inspired Ørsted, but that's just a speculation. I'm not sure about it. But Columbus, when he was traveling over the earth from one side to other, he noticed that obviously the compass was quite in use at that time, and he noticed for the first time that there were deflections when he was moving from west to east. So he realized that something is happening with the field. Obviously people weren't aware that what exactly this field is, whether it's exactly coming from the uh, earth or not, because it was after Columbus traveled it was realized that, or maybe explained that earth actually acts like a magnet. So it was after Columbus realized that there are some kind of deflections in the compass. He realized that people realized that basically earth itself has two poles and has sort of as we have seen that it has a magnetic field lines. So you can see that even in the Ørsted experiment, he's trying to play with the compass and see how it exactly the compass behaves. And we have seen that he takes the compass from one side to other and he sees that the deflection is somewhat different and not exactly attractive, as sometimes it's aligned towards or sometimes it's opposite.
So I had two comments to make. One was that although it's something which we do not have any written proof for, but it is being talked about that including Columbus, many explorers when they are on their sea voyage, they observe that not just like it's much after how people observed that there's an overall magnetic field which the Earth has, but also the fluctuations in the needle itself, which were correlated with how with if there was lightning in the sky. So this is where I would say could be potentially one of the interesting observations that people
Right,
noticed
right,
how
right.
I mean we could at least now say that this was one of the first observations to say that electricity and magnetism could show relations.
And lightning.
And lightning, yeah. So
I think I
if
think I think one of them was the Northern Lights, but I'm not sure if it was the first one.
hmm,
The
yes.
Northern Lights were the first ever lightning kind of effect due to
Mhm.
magnetic field of the Earth.
Do we know when these are first discussed, the
You mean
auroras?
you mean the date? You mean?
Hmm.
Yeah. So as far as I remember, I think it's around 1700s, 1710s or something like that, when some astronomer observed aurorae and different magnetic effects.
So I had another thing to bring up about how attraction and repulsion we're talking about the idea of attraction and repulsion. So I would want to put it as a remark, and also about, the aha moment of how things look here. That since here is the time when Ørsted talks about how it doesn't seem to be an attractive or repulsive kind of force. What I think about now is that if we talk about compass and we use magnets, what we observe is that a certain pole has attractive features and the other pole has repulsive features. So we only had observed attractive and repulsive forces in magnetism, whereas when we look at Coulomb's, for example, Coulomb's study on charges, we again talk about how attraction and repulsion takes effect. And this here, the fact that this does not look like an attractive or repulsive force, and as we are talking about here, seem to be in spirals or in circles. Now, this is where I feel this is the real scientific moment where we can see how something where we had only observed science of attraction and repulsion, we're observing a new science which is the interface between electricity and magnetism, and hence this makes it rather interesting, and this is what I liked a lot about this.
Wait, I don't really understand your point. What do you mean that there's no kind of attraction or repulsion? Because see, at present moment we know that it's actually a magnetic dipole interacting with magnetic field. Magnetic dipole as in a compass needle interacting with a magnetic field of the current carrying wire. So technically it is a force. It's just that whether it is attractive or repulsive is position dependent.
I would beg to differ because, well, now that we already know the science, if we have a wire and we're looking at the magnetic field is in circles and never either towards the wire or away from the wire. It's in a tangent to the wire. And hence, this is what I mean when I say that it is neither attractive
Okay,
nor
okay,
repulsive.
I see.
Yeah.
So yeah, I think all the attraction and repulsion that was talked before this paper was always in the line of contact. So attraction or repulsion happens in the line of contact. There are 2 points. There's a line of contact. So attraction or repulsion happens that way. So by saying that this is not a simple attraction or repulsion, when Ørsted said that it's not attraction, I think he meant that it's not line of contact, hence not attraction, because so far everything by attraction they meant attraction and line of contact. But later now we realize that it is attraction, but just in not line of contact. Later now we realize that there is something called field, and there's a field line that shows what is the direction of attraction, and it's still attraction but just not in the line of contact. And yeah, regarding your comment, Pratyush, are you sure that they had a concept of electric field before 1820?
No, there
Because-
wasn't any
because-
concept of electric field.
Yeah, so because you were saying that before this paper there were some correlations between electric field and fluid, which I'm
Uh,
not very certain about, because I don't think there was a concept of electric field in first case, because they were just starting to realize that charges move, and that's called electric current. And from there, directly coming to a concept of electric field is such a big leap. I wouldn't assume that it was present before Ørsted's paper.
Yeah, you are right.
And-
You are right.
So I think the concept of electric field and relating it with fluids motion was pretty later. And also regarding your comparison of how Ørsted might have come up with the concept of spirals by comparing it with the observations of Columbus, I find it very amusing that at no point in the paper Ørsted calls the ends of needles as poles. He keeps calling them as end of a needle, but never as a pole. And I'm not sure how well they understood magnetism and the concept of poles of magnets at that point of time. But in case if Ørsted has realized that this spiral has something to do with the spiral motion, the declination, how Columbus observed his declination on his compass when he was traveling around the world, he would have definitely come up with at least a proposition that this wire that is carrying electric current is acting something like a magnet. He never came up with that. From his paper, I assume he's a pretty smart guy. He came up with really smart conclusions from certain observations. I would guess if he had observed the correlation between the spiral he has been observing, the spiral effect he's been observing around this wire, and the spiral that Columbus observed, he would definitely have come up with the conclusion that this wire is somehow acting like a magnet. but that hasn't happened until later. Ampere realized that a current carrying wire can affect another current carrying wire. It doesn't have to be a magnetic needle. When he started observing that a current carrying wire can affect another current carrying wire, and obviously Ørsted realized that there has to be magnet involved, because any other normal needle can't do this. A brass needle which is not magnetized can't do this. And Ampere is the one who came up with the concept that this wire that is carrying current is creating magnetic field or magnetism around it. So I think Ørsted, yeah, definitely Columbus had this spiral effect published or announced or discussed way before, but I don't think Ørsted has related that to or inspired from that. But yeah, it would have been amazing if he had. Things would have been so much faster. It would have taken 10 less years to realize that what this phenomenon is actually that moving charges create magnetic field around it. It would have been observed by Ørsted itself if he was, able to relate it. So I think, yeah, on a side note, I really believe that it's very important to read or realize or know more about stuff happening in fields other than your own field in research. Although back then everything was natural philosophy and everything was a related field, even now I think if by reading or knowing about something which is not very related to our own field would give us a lot more inspiration and it makes it easier to bring out conclusions, or it's basically food for thought.
Right.
Yeah, it would have been amazing if Ørsted had made this relation.
Yeah. Can I ask something?
Yeah, sure.
Maybe I got it wrong. But wait, are you saying that Ørsted wasn't looking for magnetism when he was doing his experiments?
No, I say he had a magnetic needle, but he didn't realize, he didn't come up with a conclusion. He didn't realize that this wire, which is carrying current, is creating magnetism. He called it electric conflict, that it's creating electric conflict and that can affect a magnetic object, but he didn't realize that what is happening is it's creating magnetism.
Yeah, but then he was looking for magnetism, right? Because I think I read somewhere, I think I have that document as well. It was during his lecture on galvanism and magnetism that he demonstrated this.
So his lecture was about electricity, galvanism, and magnetism. He was dealing three different concepts. He was teaching three different concepts, and he happens to have both galvanic apparatus and a compass, because he's teaching both things in his class. He happens to have both of them, and he observed the effect of this galvanic apparatus on a compass. But that doesn't mean he realized that it was magnetism.
Oh, okay. I see. Because I was of the impression that he was always looking for, or he was kind of aware.
I don't think he was trying to unify it. He just happens to find something, observed something interesting, and then later realized that it's unifying electricity, galvanism, and magnetism. But I don't think he was trying to do it.
The reason I say this is because he was always trying to, he was aware that there are forces which are analogous to Newton's and Coulomb's law, like they're 1/r force. And there are certain categories of forces which do not obey that. And he had a certain intuition for that. And he was also, I think he spent quite some time with a German philosopher.
Yes.
Yeah, right. And they wanted to sort of give a better explanation of light and electromagnetism. And by the time that Volta came up with his cells, the battery and stuff, they were well aware that current carrying wire radiates heat, and it radiates heat in all directions, irrespective of, like, it is isotropic basically. So Ørsted knew that there existed a force which is similar to this, like similar to in a way that it is not acting along the direction of current, but in the in somewhere in the opposite direction or in the plane perpendicular to what is happening. So I think he was always sort of trying to look, and he knew that this is in some way related to magnetism, because he was working with metallics and magnetic needles. He knew like if you have a natural magnet from the environment, you can attract those magnetic needles. So he knew that whatever acts on these magnetic needles has to be magnetism. So I feel that he was always looking for magnetism, and he was just trying to put his intuition of the heat radiation from a wire to the magnetic field by a current carrying wire. What do you guys think?
Yes, I agree that Immanuel Kant was so. Ørsted did his doctoral dissertation on Immanuel Kant's philosophy, and he reinterpreted that Kantian thought as and subscribed to the concept that there exists a fundamental unity among all the forces of nature, or among all the phenomenon of nature. So he was always trying to unify all the phenomenon he observed, and he did before this paper in 1820. He did write about how uh, electric current can produce heat and light, and both also in circles or spirals around the wire. And he did realize that this magnetic effect is also in something similar in a circular or a spiral manner around the current. But from at least from the tone of his paper, I'm still suspicious if he was intentionally looking for it, or if he observed it and then realized that it agrees with his line of thought. And I still believe that he realized that this wire had a magnetic effect, but does not necessarily mean he realized that this wire was generating magnetism, or magnetic field as we would call it now.
Oh, but then what did he refer to as those spirals then?
He referred to it as electric conflict, and he says this same electric conflict, or he believed that the same electric conflict is responsible for all the three phenomena: the heat phenomena, the light phenomena, and the magnetic phenomenon around this electric wire. He called it the electric conflict. But now we know that the heat and light is produced because of the resistance of the wire. That has nothing to do with the electricity passing itself. And the magnetic field is obviously because of when charges move, it creates magnetic field around it. So we kind of disentangle the electric conflict, the word electric conflict he used, into magnetism and resistance and everything related to this phenomenon of resistance. But I think he wasn't very sure, at least from the tone of his paper. I interpret as he wasn't sure that it was a magnetism that's being created. He called it the electric conflict. So since we established that Alessandro Volta was the first inventor of battery, and one of the primary parameters that you use to quantify battery, to say how good a battery is its voltage. And I'm not sure if they had this concept of measuring voltage, or the concept of voltage itself, back in 1820, because in Ørsted paper he mentions that a smaller apparatus, by apparatus he means battery, will also provide similar results if it is strong enough to heat a metallic wire. So I think he's trying to see the power or the capacity of the battery by checking if it can heat a metallic wire or not. So I think they didn't have the concept of voltage back then. But what do you think, based on the description of the battery he gave in the paper, what do you think would have been the voltage of this battery?
So, I personally cannot speak about the voltage, but given his observations about the current, I did some calculations to get an idea of what current we can expect from this apparatus. And as we generally study the magnetic field of current, my calculations tell me that it should be at least an ampere worth of current flowing through the wire, an ampere to 10 amperes of current which should flow through the wire. And given it's a conductor, um, I would say the voltage can be expected to be order of volts or tens of volts max.
Yeah, regarding what you were saying earlier, Bhavesh, you said that Alessandro Volta was first, when he created a voltaic pile, he was the first to generate some, as you call it, steady flow of current. He had some steady flow of current in his wire. How long do you think that lasted? I mean, every battery has a discharge time. After a certain time, it can't produce electricity anymore. So, how long do you think the first voltaic pile could last?
Uh, so this is again very speculative of what I thought. So the fact that he was observing something like he was able to last the experiment long enough to observe a spiral kind of magnetic field.
No,
My
no. Not necessarily about Øysted's apparatus with him, but I'm talking about the battery that Volta created himself. For the initial stages of voltaic battery, how long do you think those batteries lasted?
So again, I have an unverified source on this where I read it lasted in the order of tens of minutes, max.
That's pretty good.
Yeah, that's a good.
If you knew that you could increase the lifetime by increasing the concentration of the solution, or putting a bigger rod or something, or
I
having a
think
less
also
he
it
keeps putting.
depends on the type of rod you choose. I think it depends on the type of the rod you choose also, because it should be the difference between the conductance of two rods that matters a lot. Right now, in most of our batteries, I think we use copper and zinc, if I'm not wrong. In the
Yeah,
normal
that's right.
battery, everyday batteries
That's right.
we use, I think it's copper and zinc. I think that has pretty good.
Mhm.
I wouldn't guess that Volta came up with copper and zinc in its first attempt. It would have tried something else earlier.
Yeah, and also to add to Aditya's comment on the concentration. So given that when he was mentioning about at least how Ørsted used the voltaic cell in his experiment, he was very precise on what concentration of hydrochloric acid or sulfuric acid, I'm not sure, either of these two, he used in his apparatus, and he was very specific about the concentration. So I would suppose that there was some amount of calibration done on how the variation of concentration works with the
Yeah.
lifetime or the current provided by the
Exactly.
battery.
So if he wanted to
So,
observe
yeah,
a longer current, he would
yeah.
just increase the current concentration. So I don't think it matters that much the time.
So yeah, I think Oyster had sulfuric and nitric acids. He mentioned the quantities pretty precisely, but I think it was intended to make it easily repeatable, because so that someone else can repeat. Because he also talks about the angle of declination. It was 45 degrees when it was parallelly placed at a certain distance from the needle. So I think he was trying to be precise about all the numbers, because it has to be repeatable by someone else and to verify it. And do you think a person can repeat the same experiment at their home? Because right now everyone has access to batteries. But do you think it's safe to connect a wire between the two terminals directly? It's basically like shorting the battery.
Now, this is where things get rather silly. People do all kinds of experiments at home. So
Yeah,
at
disclaimer:
least
we're not promoting any such doing at home. I don't think it's safe to connect two terminals of a battery directly by wire at home. So please do not try it at home.
so in a safe laboratory experiment, well, we can indeed use a 1.5 volt AA battery or AAA battery to connect it for a wire. However, it is unsafe because, as we said, we need high amounts of current. So, in fact, while doing the calculations, this is where I observed that when he was talking about a 45-degree declination, this would mean that the magnetic field has to be comparable to the magnetic field of the Earth itself, and hence that's where the current to be order of amperes come in. So I agree that if you try to come in if the setup comes in human contact, since the battery is a very less power delivery source, it cannot cause immediate issues. However, it is still unsafe, as we already mentioned. However, this experiment can be done in a laboratory given enough safety measures, I suppose, and that is also done in some experiments. I'm sorry.
Yes. I think there are a lot of YouTube videos demonstrating this experiment themselves. I think they do it in certain high schools all around the world as well. But hypothetically, if there was no resistance for the wire, this is really bad, because the battery will basically explode. But thank God they didn't know the concept of resistance, but everything they had in their hands had resistance in it, and that kind of kept it safe for them. It's happy that they're still alive because of that.
Otherwise, we would have seen something like Baghdad's electrocution possibilities.
Like the everyday substance that we have, say like an aluminum wire. Do you guys know what is like the conductivity or something? Then maybe we can guess. Maybe like a 10 centimeter of wire, how much resistance it would have.
If you're assuming a very, very thin thickness, so I remember from some experiments it has to come of the order of an ohm, or like somewhere between milliohms and ohms, if it is say 2 mm, 3 mm thick.
Okay, yeah.
And
So
as
it's
we go
per
thinner,
meter or per centimeter?
I would say something like 10 15 centimeters of wire, because some experiments are generally done in high school or bachelor's, I'm not sure, but this should be the order of it could go between ohms, and if we keep going thinner, we can attain tens to hundreds of ohms or higher. And that is where the calculation came in, that by an estimate, if we are using a very highly conducting wire of sufficient thickness, we can expect order of volts for our voltaic cell, which we originally had.
Wait. By the way, you said the magnetic field has to be comparable to the Earth's magnetic field. How much is Earth's magnetic field?
So the Earth's magnetic field is around 50 micro Tesla.
Teslas.
Yeah.
Okay.
10 to the power minus 5.
10 to the power minus 5 order. Yeah. And hence now this is where the 45 degree comes in. So when he said that he placed it directly below the wire, there was a 45 degrees, and which would mean that the component of the magnetic field and the component of the field by the conductor is comparable. And that was how we could estimate it.
I see.
And I find it very interesting that on his first, accidentally he ended up having 45 degrees. I don't think he was trying to compensate Earth's magnetic field or anything like that. He just tried with whatever galvanic apparatus he had, and it so happens that it generated exactly enough magnetic field to compensate Earth's, and then it was exactly 45 degrees of declination. I find it really amusing.
But it's see, because the magnetic field direction is changing from minus what should I say, the angle of deflection is minus 80 to plus 80, so there has to be a 0, there has to be a 45 or all the angles. So as in
No, I think to rephrase Vidya's statement, so what he did was he had placed the wire in the direction of Earth's magnetic field, so that your compass without any current is the compass needle is parallel to the wire, and from this angle we observe a 45 degree declination, which would mean that the magnetic field components are comparable. So this is what was accidentally probably observed, or maybe he altered the chemical composition, the HCl, such that he gets something like a 45 degrees.
I don't think
We
he
can
needed
only
to do that.
speculate.
He already realized that it also depends on the distance between the wire and the middle, so he can just move it far apart to get the 45 degrees. I don't think he had to do all the chemical composition change.
As long as it is strong enough.
Yeah. So yeah, moving on. Do you guys know who he is referring to when he says that some celebrated philosophers tried something similar earlier? But I find it really, really interesting that these celebrated philosophers, so-called, were trying it in a very different way. They had a wire attached to only one pole of one terminal of a battery, not both the terminals. So I mean, like, I don't think they understand how a voltaic pile works. I don't think they understand how a battery works or how electric current works back then. But then, yeah, that's how people realize, that's how the science happens. But yeah, I find it really interesting that the so-called celebrated philosophers were trying with just connecting one wire to one end of the terminal and so on. Do you guys know who is referring to when he says celebrated philosophers?
No. They're not celebrated, so much celebrated after all. Who are those? Who are they?
And yeah, that's something I find really, really shady, because these papers back then, they had no references, there had no citations at the end of the paper, so there's no way to find out who is referring to. And I couldn't find any particular celebrated philosophers as such. But yeah, as we've mentioned already a couple of times, I think it could be Romanossi, but I'm not sure it's Romanossi, because Ørsted himself claims that he didn't know about Romanossi's paper until a lot later in 1822, when someone else pointed to him that there was an Italian newspaper article about something similar published by a guy called Gian Domenico Romanossi. I think he was a judge, and also he was working in law primarily, but because everyone who was working in philosophy had some interest in natural philosophy and was working on such stuff all the time. But yeah, Romanossi definitely could fit into this model, because he was I could find a version of his Italian paper and his English translation, and he was definitely working on something like electrostatic, because he had only one, so he was using silver wire, not a copper. So he had a silver wire attached to one end of the terminal of a battery, and at the other end of this wire he had a silver ball. So he believed that this generated some static electricity or static electric charge in this ball, and he put a compass near this ball and he observed what effect it had. So he was mostly testing out the electrostatic effects on a magnet or on a magnetic needle, not electromagnetic. And if you think about it, it will have a effect, because electrostatic, after all, is creating electric field in our sense, and magnet is also made of metal, so it had electric charges in it. It has electric charges in it, so it will have an effect. It will have an angular declination, but that's definitely not with magnetic effect. It's purely an electric field, an electric field having an effect on a metal, just like electrostatic will have a effect on a metal needle, not necessarily a magnetic needle.
I'm not sure about the feasibility of your explanation, given how we look at magnets. I would say the enclosure of a magnetic compass is generally metallic, which would provide some extent of shielding. And second, the extent of magnetic fluctuations, electrical fluctuations you would expect in something like a compass would be less. Now, talking about what Romanozzi had found out in his experiments. So if we look at the 1830 discussion by Ørsted himself, he does acknowledge Romanozzi's experiment, and given that he acknowledges it in a very odd manner, where he does say that if this research had indeed gained attention, we would have saved 15 years or so of time for the discovery of the fact that magnetism or at least magnetic field is observed from current carrying wires. But he also says that the experiment was not matured enough, or could not give the exact kind of results, because he claims it is not the exact same setup. As you say, it's an open setup. I would say he does acknowledge it. Yeah, sorry.
I don't think Ørsted is referring to Romanozzi when he says celebrated philosophers. I don't think so.
Yeah, so that's true. What I mean is, in a paper which is about 10-15 years after this paper of 1920, he acknowledges Romanozzi's work. In his actual paper, I would not guess he's acknowledging Romanozzi in the celebrated philosophers.
Okay. Anyway, so I think I have to point. I misinterpreted it or miscommunicated it. That neither Romanozzi nor Ørsted, in their the experiment, the primary observation that they're describing, do it with compass inside a compass. They remove the magnetic needle and observe the effects directly on the magnetic needle. It's not inside a compass enclosure. And from so I obviously we are going to link the paper I found about Romanozzi's paper, so both the Italian version and the English translation. And and he clearly mentions connecting only one terminal of a battery through a silver wire to a silver blob, as he calls it, or the English translation calls it. So I don't think he was observing the effects of electric current. He was purely observing electrostatic effects on magnet. And the declinations he observed are obviously not as prominent as Ørsted, because, as you mentioned, the electric effects here are not really prominent to be observable. But he was lucky enough to have good enough. I think it also has to do with how big your silver blob is, because that defines how big your concentration of electric charge is here. If you have a really good concentration of static electric charges, I think you could have a slight deflection in the needle. And if Romanozzi had observed this with a non-magnetized, a normal metallic needle, he probably would have identified that this is not magnetism and this is purely electricity, which he didn't.
I would still want to argue your point on why charge. So I can understand that in the brief moment where charge is accumulating on the silver blob, we would observe some fluctuations. However, the fact that charge itself cannot induce any fluctuations if it's static, because
it's called charge inducement. Because, for example, the very basic, most common example of static electricity that you are taught in school, you take a comb, rub it against your hair. So now it has a charge. It has static electric charge, right? Now put it near a set of papers which are completely neutral. They get attracted, right? So they move.
That is if we are creating motion, right? If we are creating motion, you're talking about fluctuations in the needle.
No, it's not fluctuation. It's just single deflection. It's not fluctuation. It's not a constant motion. It's just one. And even in Ørsted paper, he wasn't observing a fluctuation. He just saw that there's a declination. That's it. As at the moment you switch on the wire, the electric current in the wire, the magnetic needle started declinated into 45 degrees, and it stopped there. There's no fluctuation as such. So I think Romanossi deserves certain credit for himself, but definitely not credit for unifying electricity and magnetism, because there was no magnetism in his observations.
Okay, so Sagar, as you were saying, I do not agree with your idea of how electrostatics was responsible for the deflection in the needle when it comes to Romanossi. Because from what I understand, it was the momentary discharge, or rather the charging, of the electric blob, which caused a deflection in the needle, and hence it cannot be given to the pure nature of electrostatics here. It was rather that as soon as one terminal was connected to the blob through the electric wire, that is when the flow of charge caused deflections in the magnetic needle, and that is what Romanossi observed. Of course, because it was not flowing current, we cannot exactly say that this was current caused because of magnetic current causing
Constant
magnetic field. Yeah.
So you say that Romanossi observed the effect of varying magnetic field even before Ørsted observed the effect of a constant magnetic field.
I would say so, yes.
Yeah, technically, I think that was the case.
Okay, I would still, I'm still not convinced that I still interpret Romanossi's effects as purely electrostatic, but we can both like put our sources in the Reddit, and probably that will be a good place to discuss about which interpretation makes more sense. So yeah, going ahead, so I'm still a little confused because not just Romanossi, even Ørsted mentioned in his paper that there were some celebrated philosophers who were trying some experiments like this, but with only one terminal being connected. So I'm a little confused about how between this 1800, when Volta created the first battery, and 1820, when Ørsted found out the magnetic effects of current carrying wires, how exactly were they testing if the wire is actually carrying current or not? Between 1800 and 1820, I have a feeling that 1820's experiment by Ørsted is the first ever kind of test to see if a wire is carrying current or not. You can just put a magnet near it, and if it deflects, then the current is flowing in the wire. But I wonder if there was any other way of testing before Ørsted experiment.
I think I have heard of some of the tests.
Mm-hmm.
I think one of them was animal testing. They used animals. One of them was, I think there was something back in around 1800s called tongue test,
Okay.
in which they put the terminals in their tongue, and even if a slight of, so to speak, agitation would.
So if you put only one wire
Mhm.
attached to one terminal of the battery, and if you put it to the tongue, do you think there will be any agitation?
No, I'm saying if you
Like
have
it
two
was in the silver
terminals-
blob in Romanossi's
if you have two
experiment?
terminals. No, I'm saying if you have two terminals, and if you want to see if there is a complete circuit or not, and then you put both the terminals in your tongue.
To answer your question, Sagar, I would say you would not detect something because your resistance, if you are using earth as the second terminal, the current is so low that your sensors will not trigger to know that
I think-
current is flowing because it is
I
much
think
smaller.
this tongue test was done by Volta himself
Mhm.
while
Also,
discovering this.
But I think any muscle in general would work from starting from
Any muscle.
Yeah, it does.
No, I think it's because your tongue is moist, which would cause
Because of
more
the-
higher conductivity. Yes,
Yeah.
yeah.
Right.
And it's probably salt water, is it? I think there's a good amount of salts, all kinds of salts in the saliva, probably.
Also, I'm curious about this in the voltaic pile because it is was it a paste or a liquid we were talking about?
In Ørsted voltaic pile,
Yes.
it's liquid. It's a
It's
liquid
liquid.
electrostat, liquid electrolyte.
I remember doing some electrolytic experiments where we have seen some sort of bubbling happening near the electrodes when the charge is flowing.
Electrolytes?
If
and they-
if it heats up, probably.
I'm not sure, but that
But why?
seemed like one of the ideas of if there's a continuous flow of current, probably there might be some observable physical changes in the cell.
Oh.
Yeah. I'm not very sure about this, but I believe that there
Yeah,
are some
so-
changes which I observed.
There are molecules which are moving inside the electrolyte, so the motion creates heat, and I think the heat could.
I think it's more of a chemical reaction, right? Because you have
It is, I think.
ions being formed because from metal to ionic forms. So one is being deposited, the other is being is mixing into the solution. So I think some chemical change would release probably like water molecules
H2 or
and
something
hence,
like that.
yeah.
So that probably depends on the chemical composition. Not every kind of electrolytes would probably generate this, and I hope
But
they use
as of now,
safer.
we have only one electrolyte which they had used, electrolytic setup.
Oh yeah, I probably
Yeah.
yes.
Yeah.
Yeah, we already mentioned that there were no sort of any references or citations in the paper, and which was one of the reasons why we couldn't figure out who these celebrated philosophers were. But I also wonder how peer review system worked back then, because Ørsted stressed a little on how he got it verified by esteemed people. He mentioned the names and the professions of multiple people that he got the entire setup verified by. But it sounds a little weird that the author himself gets the final authority on who verifies it and stuff like that. So I wonder how peer review worked back then. Probably it was handled by the Royal Societies of all the European countries, but I have no clue.
Like the first referee system was put in place by the English Scientific Society in the early 19th century. And the idea was given by a Cambridge professor who said that Royal Society of London should have some people called some scientific publicists who would look over what goes on into the journals and what the public reads and stuff.
And also, Ørsted wasn't a pure physicist himself. He was a natural philosopher, definitely. And his primary works earlier were in pharmacy and in philosophy, I assume. But trying his hand at how theory works, he proposed that this phenomenon could be explained by supposing that some sort of negative electricity moves in spirals along the wire, which doesn't make complete sense to me because the negative electricity that we understand now, is being moved in the wire and not around the wire in spirals.
I think he could mean something related to direction, negative electricity, but I'm not sure.
Yeah, probably the direction, but how did he come up with negative electricity moves in a spiral? Oh, or maybe he thought it was purely electric effect, where there is electricity moving in wire, a positive electricity as they assumed back then, and a negative electricity moving along the wire,
I
which
understand
is
your point.
doing an electric effect only on the compass needle. But I'm still surprised, because
Okay.
then
So I
it doesn't
think
make sense because he already verified that this is not purely electric and it had some magnetic effect because he did with a normal non-magnetic brass needle and then observed that there was no effect. So I think he was trying. He was probably just speculating some
Or
theories,
maybe
but
he
this
was
is
he was saying magnetic field as a negative electricity.
That is what I'm wondering about as well.
Yeah, he was proposing magnetic field. I mean, there was no magnetic field back then, but then he was proposing that there was something like negative electricity moving along it. But he kind of contradicted himself by saying that this won't directly affect brass needle.
Something which is unexplained. He just named it as negative electricity, something like that.
Yeah, probably. And this obviously didn't last longer. And I really like how he says that he proposes that maybe using marks or figures will make things easier to understand. It wasn't very common to use marks and figures back then. It was mostly equations and theories people used to understand physics. I wonder if Newton, in our high schools, we studied a lot of Newtonian mechanics using free fall diagrams and stuff like that. I wonder if Newton came up with that, or it was some invention that some teacher came up with over the time after Newton to make things easier. But yeah, it was very smart of Ørsted to propose that marks and figures are supposed to be used to make things easier, and they do. And I wouldn't imagine that I would be able to understand how fields work without marks in my high school either.
Well, it's also notable and ironic that he did not use any marks and figures in his own paper.
Yeah, that also shows how big of a leap it is to actually be able to create marks and figures. I wonder if Ampere may used marks and figures already in its time, but that's something we can check later and discuss on the Reddit again. Yeah, I think that's all the comments we have so far.
So, wrapping up the current paper, we see that the whole experimental setup is quite easy to explain in terms of our current knowledge of physics, which is nothing but a interaction between the magnetic field created by a current carrying wire and the magnetic dipole, which is nothing but our compass needle. But all this knowledge took its time to get into this level of understanding. For example, 2 years later, this experiment, Ampere came up with a mathematical law to describe the magnetic forces between two current carrying wires, which is nothing but became later the definition for what exactly is 1 ampere. And so we can see that we are using force to quantify the amount of current passing through a wire. Then a decade later, Faraday came up with his law of electromagnetic induction, which is nothing but that a changing magnetic flux induces an electric current, which is sort of the opposite of what exactly is happening in this experiment. So next, going with the major philosophy of unifying electricity and magnetism, James Clerk Maxwell came up with his equations. So with his equations, we can actually sort of see that the electromagnetic wave propagate with a speed which coincided with the speed of light, and I think this was sort of could be a good hint that light is nothing but an electromagnetic wave. And we can also, according to our current knowledge, as we know that special theory of relativity is actually what deeply connects electricity and magnetism, which was even though developed much later, but as we can see that the whole philosophy of unifying different laws of nature always stays in the mind of scientists, and still people are working on different unifying theories. In 1825, Ørsted produced aluminium for the first time, which is quite cool. And being a first modern thinker, and he also named something called as a Gedanken experiment called the thought experiment, which was later used by lots of other people and scientists. He also started the Society for Dissemination of Natural Science, which was basically dedicated to making science more accessible to common people who are not that closely related to the whole group of scientists. So I think for him also the spreading of science was quite important, and we also abide by the same philosophy.
Yeah, so though we have as much passion as Ørsted to spread science and make it more accessible to public and actually change the way we think about our daily lives, we have a little disclaimer. We are all graduate students and working on this podcast in our free time. We try our best to make sure that everything we say is accurate, but no one's completely perfect. So if you find any mistakes in what we said, please let us know through either mail or on our subreddit. So we have a subreddit where we try to build up discussions on the episode, and we will be active on there. And then we hope people who have all kinds of questions and more things to add upon are welcome there. This episode gave us a lot of ideas on how we can, what are the topics to cover in further episodes. But if you have any other suggestions, please let us know. And links to everything we mentioned in this episode will be available on our website, sciencediggers.club.
With that, we conclude today's episode. Feed your curiosity, engage and explore while being open to errors, and most importantly, keep digging.